Hey guys, tonight, we're going to step into the quiet starlit realm of the impossible, a place where the familiar hum of our daily lives fades into the deep silence of space. Imagine for a moment that you're not just listening, but floating in the inky blackness, the gentle pinpricks of a billion stars, your only company. The Earth, a soft blue marble far behind you, continues its endless orbit around the sun, a rhythm we have all come to take for granted. But what if that rhythm were to be disturbed? What if something vast, something unseen were to enter our celestial neighborhood? We're talking about a black hole, a cosmic ghost, a silent gravitational force with the power to rewrite the very laws of our existence. It's a thought that might keep you awake, but that's not our goal. Our goal is to explore this thought, this beautiful catastrophe, with a sense of wonder and calm. We're not here to be afraid. We're here to understand. And while you probably wouldn't survive a real encounter with a black hole, we can explore the idea from the safety of our imagination, where everything is possible. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Now, if you're willing to share, tell me where you are right now and what time it is there in your part of the world. With that thought held gently in your mind, let's begin our journey. We start not with a bang, but with a whisper. A cosmic whisper so faint, it's almost a philosophical concept rather than a physical event. In the grand silent ballet of the cosmos, things rarely happen with a crash or a flash. Instead, they unfold over eons, like the slow, deliberate blooming of a flower that takes millennia to unfurl its petals. And so, it would be with the arrival of a black hole. It would not announce itself with a trumpet blast or a sudden dramatic appearance. It would arrive in the deep black, a ghost of gravity, an unseen thread in the fabric of space-time. Its presence would be a question mark, a subtle discord in the perfect harmony of our solar system's song. For the first many years, perhaps even centuries, we wouldn't see it. We couldn't. It is the very nature of a black hole to be invisible, a region where gravity is so strong that not even light can escape. So our first clue would be a different kind of light altogether, the light of mathematics, of careful observation, of noticing that something somewhere is just a little bit wrong. The outer reaches of our solar system are a vast, cold library of ancient history. Here beyond the orbit of Neptune lies the Oort cloud, a spherical shell of icy objects, a cosmic attic full of frozen comets and minor planets. This cloud is a remnant of the solar system's formation, a silent sentinel standing guard at the edge of our celestial domain. This is where the black hole's influence would first be felt. Think of a tapestry woven with a billion threads, each one a comet or an asteroid in its own stable ancient orbit. Now imagine a heavy invisible weight being slowly placed near the edge of that tapestry. The threads wouldn't snap, not at first. They would simply begin to shift, to vibrate differently. The orbits of these icy bodies would subtly, almost imperceptibly, begin to change. A comet that once took 1,000,000 years to complete its journey might now take 1,000,001. Another might find its path tilted just a fraction of a degree. These changes would be too small to be seen with the naked eye or even with our most powerful telescopes at first. They would be a statistical anomaly, a puzzle that would slowly present itself to astronomers. This is the first cosmic whisper, a gentle shift in the ancient dance of the Oort cloud. We as a species have a deep-seated need to see things to believe them. The idea of an unseen object that holds such immense power is unsettling, and it forces us to confront a fundamental truth, that our universe is filled with things we cannot perceive directly. The black hole's arrival is a perfect example of this. It's a journey into the realm of the invisible, where we must rely on secondary evidence, on the echoes of its presence. It reminds me of the way we understand consciousness. We cannot see it, touch it, or measure it directly, yet we know it's there because of its effects. The words we speak, the art we create, the way we experience the world. the black hole's presence is similar. Its existence would be revealed not by its light, but by its shadow, a gravitational shadow that would stretch across the vast emptiness of space. This gravitational influence, this silent shadow, is a manifestation of Einstein's theory of general relativity. At its heart, this theory says that gravity isn't a force pulling objects together, but a consequence of the curvature of space-time. Imagine a giant, stretched-out rubber sheet. If you place a heavy bowling ball in the center, the sheet bends. Any marbles you roll nearby will follow the curved path created by the bowling ball. The bowling ball is the sun, and the marbles are the planets. A black hole is like an incredibly dense bowling ball so heavy it creates a deep, steep well in the rubber sheet of space-time. This well is what we call gravity. The deeper the well, the stronger the pull. And as this incredibly deep well approaches our solar system, it begins to subtly warp the entire sheet, bending the paths of everything in its wake. The Oort cloud's slight orbital shifts are our first glimpse of this bending. It's a concept that feels abstract, but its effects are profoundly physical. The beautiful and slightly terrifying thing about this is how far-reaching this influence is. Gravity, unlike a campfire's light, doesn't diminish to nothingness. It fades, but it extends to the very edges of the universe, the gravitational pull of a single atom on Earth, however tiny, is still theoretically felt at the other end of the cosmos. It's a network, a web of connections that links everything to everything else. So when this new, incredibly heavy node enters the network, every other node, every planet, every comet, every grain of dust feels it. It's a cosmic butterfly effect, where a seemingly insignificant change in the outer solar system could have profound consequences down the line. We might first detect this through long-term painstaking analysis of the data from our telescopes. We would be looking at the orbits of distant comets, perhaps ones that have been tracked for decades, and notice a small consistent deviation from what our models predict. It would be a statistical anomaly, a number that just doesn't quite fit the grand equation. And this is where the human element, the curiosity of a scientist, truly shines. A lesser mind might dismiss the anomaly as an error in measurement, a glitch in the data. But a true scientist, a seeker of truth, would see it as a clue, a breadcrumb leading to a greater mystery. They would spend years, maybe a lifetime, trying to understand why this one comet is behaving just a little bit strangely. They would build new models, run new simulations, and peer deeper into the data, searching for the source of this subtle disturbance. The mystery would grow. Other astronomers would begin to notice similar anomalies. The orbits of the planets in the outer solar system, Neptune and Uranus, would show tiny fractional changes over time changes that could not be explained by the known gravitational forces of the Sun and the other planets. It would be a puzzle worthy of the great minds, a cosmic detective story with a suspect that is impossible to see. This detective story would be a testament to our ingenuity and our ability to understand the universe through its effects rather than its appearance. It reminds me of the search for Planet 9, a hypothetical planet in the outer solar system whose existence has been proposed to explain the unusual orbits of several distant objects. We haven't seen Planet 9, but we infer its existence from the gravitational signature it leaves behind. The black hole would be a more extreme version of this. Instead of a planet, a massive dense object with a gravitational field of immense power, completely dark and silent, yet screaming its presence through the subtle wiggles and wobbles it creates in the cosmic dance. The first definitive proof would come not from a visual sighting, but from a calculation, a mathematical prediction that would perfectly explain all the observed anomalies. A team of scientists would feed all the strange orbital data into their supercomputers, testing every possible explanation. Was it a miscalculation of the mass of Neptune, an undiscovered planet? Or was it something else entirely? They would eventually create a model where a massive unseen object with the mass of a small star was slowly moving through the deep blackness of space. The position, speed, and trajectory of this hypothetical object would be a perfect fit for all the strange data points. And then a sense of awe would wash over the scientific community. The ghost had been found. The whisper had become a name. The implications of this discovery would be staggering. Not only would we have discovered a black hole in our own solar system, but we would have done so without ever seeing it, a triumph of theoretical physics and observational astronomy. It would be a moment that forever changes our understanding of what is possible. A moment that proves the universe is even stranger and more beautiful than we could have ever imagined. It would raise 1,000 new questions. Where did it come from? Is it alone? How large is it exactly? And perhaps the most pressing question of all, what will happen when it gets closer? The quiet whisper of its arrival would be a memory replaced by the growing roar of a cosmic event unlike any we have ever known. This brings us back to the philosophical question of the unseen. The black hole is a metaphor for all the things we don't know, all the forces at play in our lives that we can't perceive directly. It's the truth behind the curtain, the answer to a question we didn't even know to ask. The silent arrival of this cosmic object is a beautiful slow-motion lesson in humility, a reminder that we are just small specks on a small planet and that the universe is vast and full of secrets. And as we drift off to sleep, perhaps we can hold on to that thought that there is a quiet, powerful mystery moving through the darkness, and it is beautiful. The cosmic whisper, the initial almost imperceptible shift in the orbits of the Oort cloud, would not remain a whisper for long. As the unseen black hole, this silent marauder, continues its slow, deliberate journey toward the heart of our solar system, its gravitational footprint would deepen. The effects, once confined to the distant icy fringes, would begin to creep inward, a cold, invisible hand reaching for the next set of players in our celestial drama. It is a slow-motion dance, a celestial waltz, where the music is the ever-present, all-encompassing force of gravity. And the next to feel this profound influence would be the outermost planets themselves. Imagine, if you will, a grand spinning top. Its rotation is steady, its wobble predictable, a perfect, elegant ballet. Now imagine a tiny, almost weightless finger, gently, ever so gently, brushing against its side. At first you wouldn't notice. The top would continue to spin as if nothing had happened. But over time, the tiny push would have a cumulative effect. The wobble would change, the spin would become slightly more erratic. This is what would happen to the orbits of Neptune and Uranus. These gas giants, vast and majestic in their lonely orbits, are our first line of defense, our solar system's cosmic sentinels. Their massive size and immense distance from the Sun make their orbits incredibly stable, a testament to the balance of forces that has held our solar system together for billions of years. But stability is not permanence, and a new powerful force would be at play. The changes would be subtle, a quiet deviation from the expected path. We are talking about a planet's orbital period changing not by a day, but by a fraction of a second over the course of a human lifetime. We are talking about its position in the sky, being off by a few hundred kilometers after a decade of observation, a tiny error in a cosmic scale that spans billions of kilometers. This is the gravitational perturbation at work. Every object in the universe exerts a gravitational pull on every other object. The planets pull on the Sun pulls on the planets, and they all pull on each other. These pulls are what govern their orbits. The black hole's arrival would introduce a new massive gravitational source, a new pull that our existing models wouldn't account for. It would be like adding a new unlisted ingredient to a perfect recipe. The result would still be recognizable, but with a new subtle and ultimately profound flavor. Astronomers armed with decades of data from telescopes like the Hubble and the James Webb would begin to notice these tiny discrepancies. They would see that Neptune's stately 165-year journey around the Sun is not quite as it should be. The data would show a slight acceleration on one side of its orbit and a slight deceleration on the other, a gentle, invisible tug of war. This is a very real concept in celestial mechanics. The existence of Neptune itself was predicted before it was ever seen, because astronomers noticed that the orbit of Uranus was behaving strangely. They calculated that a massive unseen planet must be pulling on Uranus, and they were able to predict its location with stunning accuracy. The black hole would be the new Neptune, a ghost planet whose presence is only known through the disturbances it causes. But unlike Neptune, this object would have no visible surface, no shimmering blue atmosphere, only a silent, all-consuming void. The subtle gravitational shifts would not only affect the orbits of these planets, but also their very essence. Uranus, with its peculiar sideways tilt, and Neptune, with its powerful winds, would feel a new faint pull on their atmospheres. While the effect would be incredibly small at this distance, it's a reminder of the black hole's omnipresent influence. The black hole's gravity would be an artist with a delicate brush, slowly, almost imperceptibly, altering the masterpiece of our solar system. The planets wouldn't be violently ripped from their orbits. They would be nudged, guided into a slightly different path, a new celestial harmony. This raises a deep philosophical question about the nature of a system. When is a system truly stable? Is our solar system, which has been in its current state for billions of years, truly in a state of perfect eternal balance? Or is it merely in a long quiet pause between cosmic events? The arrival of a black hole, however distant, reminds us that the universe is not static. It is a constantly evolving dynamic tapestry, and our solar system is just one small thread in that grand design. The black hole's approach is a change in the pattern, a new color woven into the fabric. The unsolved mystery here is not just about the black hole's identity, but about the true, long-term stability of our celestial home. Physicists still wonder if given enough time, our solar system would eventually tear itself apart, even without an external intruder. The black hole's approach simply accelerates the inevitable question. One of the fascinating and little-known scientific facts about this scenario would be its effect on the heliosphere, the vast bubble of solar wind that surrounds our solar system. The sun constantly streams out a torrent of charged particles, a solar wind that pushes against the interstellar medium, creating a protective boundary. This boundary is like a fence around our cosmic neighborhood. The black hole's gravity, however, would be a new kind of pressure, a powerful localized force that would begin to warp and distort this bubble. The heliosphere would stretch and bend, a silent, invisible sign of the black hole's presence. Our Voyager probes, which are currently exploring this boundary, might be the first to truly feel this change. Their instruments, designed to measure the density and direction of the solar wind and interstellar particles, might pick up on a change in the pressure, a subtle shift in the cosmic currents. It would be like a boat on a calm lake suddenly noticing a new powerful undercurrent, pulling it in a different direction. The effect on the heliosphere is a good example of the cascading nature of this event. A disturbance at the very edge of our solar system, an unseen object, creates a ripple that travels inward, affecting everything it touches. It's a reminder that nothing in the universe exists in a vacuum. Everything is connected, and the actions of one object, no matter how distant, can have a profound impact on another. This is the essence of gravity, the invisible hand that links us all, from the smallest dust motes in the Oort cloud to the mighty sun itself. As the black hole continues its journey, the tiny changes in the orbits of Neptune and Uranus would become easier to measure. Astronomers, having now confirmed the existence of this silent visitor, would be able to track its path with increasing accuracy. They would predict its trajectory, its speed, and its closest approach to the sun. This is the moment when the cosmic whisper begins to become a hum, a low resonant frequency that everyone, from the professional scientist to the amateur stargazer, can begin to feel. The questions would shift from, "Is it there?" to, "Oh, what will it do?" and "How close will it get?" The initial discovery, a triumph of abstract thought and careful observation, would be replaced by a new, more immediate sense of awe and apprehension. Remember how we talked about the Oort cloud scattering its comets like dust? The same tidal forces that caused that scattering are now acting on the planets. Think of the planets not as solid, unyielding spheres, but as vast, semi-fluid bodies. The tidal forces of the sun create tides on Earth, pulling the oceans and even the solid ground. The black hole, with its immense gravity, would create its own far-reaching tidal forces. At this distance, the effects on Neptune and Uranus would be minimal, perhaps a slight increase in their atmospheric turbulence or a subtle shift in the shape of their gravitational fields. But it's a foretaste of what's to come, a gentle, almost affectionate squeeze that hints at a terrifying strength. The silent arrival of the black hole is a slow, elegant unveiling of a cosmic truth. It shows us that our solar system, a place we thought we knew so well, is full of hidden depths and unknown forces. It reminds me of the way we learn about ourselves. We think we are a complete stable system, a fixed point in the universe, but then we encounter a new idea, a new person, or a new challenge, and we realize that we are not as fixed as we thought. We are constantly changing, our internal orbits being subtly shifted and recalibrated. The black hole's journey is a mirror for our own lives, a quiet reminder that change is the only constant. And as we feel the gentle invisible tug on the outer planets, we can find a strange comfort in that thought, a sense of belonging to a universe that is always, always moving. The subtle shifts in the orbits of the outer planets, the gentle, almost invisible bending of the heliosphere. All of these are merely the first tremors. They are the initial notes of a deep resonant chord that would soon sound across the entire solar system. As the black hole, this celestial wanderer, draws ever closer, its gravitational influence ceases to be a distant, theoretical puzzle and becomes a tangible force, a physical reality that would announce itself not with light, but with a ripple in the very fabric of existence. We are talking, of course, about gravitational waves. Imagine a still, placid lake on a windless day. The surface is a perfect mirror reflecting the quiet sky. Now imagine a stone, vast and unseen, being dropped into that lake miles away. The impact wouldn't create an immediate splash that you could see, but it would send out ripples across the surface of the water, an outward moving disturbance that, though small, would carry the memory of the event. Gravitational waves are the universe's version of these ripples. They are not waves of water or sound, but waves of space-time itself. According to Einstein's general relativity, any accelerating mass creates these ripples, and the more massive and dense the object, the more powerful the ripples. Two black holes, or neutron stars, spiraling into each other create a cosmic crescendo of gravitational waves, a soundless scream that travels across the universe at the speed of light. A solitary black hole moving steadily through the deep blackness of space doesn't create a strong, loud chorus of these waves. Its journey is more like a silent, powerful ship, cutting through a calm ocean, creating a bow wave that is felt, but not seen. As it gets closer to our solar system, however, its interaction with the sun and the planets, the subtle gravitational tug-of-war, would create a new kind of signal. It would be a low, continuous hum, a constant, gentle distortion of the space-time around us. And we have instruments designed to hear this hum. In our current world, we have giant, incredibly sensitive detectors called LIGO laser interferometer, gravitational wave observatory. These observatories are essentially two long perpendicular tunnels with mirrors at the end, set up as a massive laser interferometer. A laser beam is split in two, sent down each tunnel, bounced off the mirrors, and then recombined. If a gravitational wave passes by, it stretches and squeezes space-time itself, causing one tunnel to become ever so slightly longer and the other ever so slightly shorter. This minute change, a movement smaller than a proton, is enough to throw the recombined laser beams out of sync, creating a telltale signal. We've used these detectors to hear the cataclysmic mergers of black holes and neutron stars light years away. But what would it be like to have the source of these waves right here in our own backyard? The arrival of the black hole would be a new kind of sound for these detectors. It wouldn't be a sudden high-pitched chirp of a merger, but a continuous low-frequency signal that would steadily increase in strength as the black hole gets closer. This would be our first definitive, undeniable proof, not just of its existence, but of its physical properties. By analyzing the characteristics of the gravitational waves, their frequency, their amplitude, and how they change over time, scientists could calculate the black hole's mass with incredible precision. They could determine its spin and its exact trajectory. This would be a moment of pure scientific awe, a triumph of human ingenuity, and our ability to listen to the silent symphony of the universe. This brings us to a fascinating and little-known fact about gravitational waves. They are not the same as electromagnetic waves like light. They travel through space-time, not in it. This means they are not affected by matter in the same way. A gravitational wave from a distant black hole merger can pass right through the Earth without us ever noticing, except for the tiny, almost immeasurable wobble it creates in our detectors. It's a ghost passing through a ghost. This property is what makes them such a powerful tool for observation, as they can carry information from parts of the universe that are completely opaque to light. The black hole's arrival would be a beautiful live demonstration of this principle, a chance to study a cosmic object in our own solar system, with a sense we didn't even know we had until recently. The discovery would be a great paradox. The black hole itself is defined by its ability to trap light to be a complete and utter absence of information from an electromagnetic perspective. And yet its presence would be screaming information to us through the medium of space-time itself. It's a reminder that the universe has many ways of communicating, and we are only just beginning to learn its languages. The black hole would be a master teacher, using its very silence and darkness to illuminate the most profound truths about gravity and the nature of reality. The sheer scale of this event is something to quietly contemplate. The gravitational waves generated by the black hole's passage would be a constant, gentle tremor across our planet. We wouldn't feel it, of course. The human body is not built to perceive such subtle shifts. But our instruments, our beautiful complex machines would feel it. It would be like a cosmic heartbeat, a new pulse in the rhythm of our solar system. The Earth would stretch and squeeze by an unimaginably small amount, a constant, gentle breathing that would be the silent song of the black hole's approach. This would be a perfect example of a scientific, unsolved mystery. While we understand the physics of gravitational waves, we still don't fully comprehend the nature of space-time itself. What is it really? A physical medium, a mathematical construct. The black hole's passage would give us new data points, new questions to ask about the very substance of our reality. The philosophical implications are profound. The black hole's arrival, confirmed by these gravitational ripples, forces us to re-evaluate our place in the universe. We often think of our solar system as a self-contained unit, a clockwork of planets and stars. But the black hole reminds us that we are part of a larger, interconnected cosmos, a vast ocean filled with currents and tides we are only beginning to chart. The gravitational waves are the proof of that connection, the invisible umbilical cord that links our small corner of the universe to the grand, violent, and beautiful events happening light years away. The hum of the gravitational waves would be a new kind of background noise for astronomers, a new constant to factor into their equations. It would be a new kind of celestial navigation, a way of locating and tracking an object that is fundamentally invisible to our eyes. They would be able to pinpoint the black hole's location and its trajectory with breathtaking accuracy, allowing them to predict its impact on the rest of the solar system with ever-increasing confidence. The cosmic whisper would have become a clear, loud hum, a signal that could no longer be ignored. The silent arrival would have given way to a noisy presence, a beautiful, terrifying sound that only our machines can hear. The age of silent observation would be replaced by an era of profound and startling revelation. The cosmic hum of gravitational waves, a silent song only our most sensitive instruments could hear, would grow steadily louder as the black hole continued its inexorable approach. But the ripples in space-time are only one side of the story. The other, far more chaotic and visually spectacular, would be the disruption of the Oort cloud. We've already talked about the first whispers of this event, the subtle nudges to ancient orbits. Now, as the black hole enters the inner regions of this vast icy sphere, the whispers would become a roar. Imagine a tranquil snow-covered field at night, each snowflake a frozen comet, each one in its own quiet, stable place. The field stretches for billions of kilometers in every direction, a deep and silent wilderness. Now, imagine a powerful, invisible hand sweeping through the center of that field. The snowflakes wouldn't just shift. They would be violently flung from their resting places. They would scatter, not in a gentle drift, but in a chaotic, brilliant spray of ice and dust, like a shaken snow globe. This is what would happen to the Oort cloud. The black hole's immense gravity, now a powerful local force, would begin to tear at the fabric of this ancient frozen shell. The tidal forces of the black hole would be the primary engine of this destruction. Think of tides on Earth. The moon's gravity pulls on the side of the Earth, facing it more strongly than the far side, stretching our planet into a slight oval. This stretching creates the high and low tides in our oceans. Now imagine that same principle, but with a gravitational force so immense that it could be measured in the millions of times the strength of the moon's. As the black hole enters the Oort cloud, it would stretch and pull the icy bodies with a power they have never experienced. The ancient stable orbits of comets and dwarf planets would be catastrophically disrupted. Some of these icy wanderers, now unbound from their quiet paths, would be flung outward into the vast, cold emptiness of interstellar space, a one-way ticket to cosmic loneliness. Others, however, would be drawn inward, their trajectories bent and accelerated toward the sun. These would become long-period comets, magnificent celestial visitors with eccentric orbits that take thousands of years to complete. We see these comets from time to time. Halley's Comet, for example, is a famous one with a relatively short 76-year orbit. But the black hole's passage would trigger a comet storm on a scale that has never been witnessed by human eyes. The night sky for centuries to come would be filled with the ghostly tales of thousands of new comets, each one a testament to the beautiful violent event that rearranged our cosmic neighborhood. This is a beautiful example of a scientific, unsolved mystery. While we understand the mechanics of how comets are formed and where they come from, we don't fully know how many objects are truly in the Oort cloud. Estimates range from trillions to quintillions. The black hole's passage would give us a chance to test those theories, to see a massive influx of comets that would allow us to better understand the true scale and composition of our solar system's outer boundaries. It would be a moment of chaos, yes, but also a moment of unprecedented scientific discovery. We would be watching our own solar system being born again in a way as a new population of comets is sent on its journey. The philosophical implications of this event are staggering. The Oort cloud is our solar system's memory, a repository of the primordial material that formed the planets and the sun. The black hole's passage would be like someone taking a giant cosmic broom to this memory, scattering it and reshaping it into something new. It reminds me of the way we deal with our own memories. We think of them as stable, a fixed record of our past, but they are constantly being reshaped and reinterpreted by the new experiences we have. The arrival of the black hole is a cosmic scale example of this, a powerful new experience that would forever alter the memory of our solar system. The sheer number of these incoming comets would be a beautiful and slightly terrifying sight. Think of all the comets we've ever seen, the ones that have graced our skies with their ethereal beauty. Now multiply that by 1,000 or 1,000,000. The night sky for years would be a constant parade of these icy wanderers, a cosmic light show. And while the vast majority of them would miss the inner planets, their sheer numbers would increase the odds of an impact. It's an interesting thought experiment, a rare and perfect blend of beautiful chaos and quiet dread. The dust and gas from these comets would also have an effect on the interplanetary medium. As they approach the Sun, they would begin to sublimate their ice, turning directly into gas, creating the spectacular tails that we associate with comets. This would introduce new material into the solar system, a constant stream of water, carbon dioxide, and other compounds. While the overall effect on the planet's atmospheres would be negligible, it would subtly change the chemistry of the space between the planets, a new cold cosmic wind blowing in from the outer darkness. It's a reminder that even in the vacuum of space, things are never truly empty. The astronomers of this future would have a new monumental task. They would be tracking not just one new object, the black hole, but thousands upon thousands of new objects, the comets. Their telescopes would be constantly monitoring the skies, predicting the paths of these celestial interlopers. A beautiful high-stakes game of cosmic billiards. The old maps of the solar system would have to be redrawn, a new reality to be charted and understood. The solar system would no longer be a tidy, predictable place, but a dynamic, exciting, and slightly dangerous frontier. The disruption of the Oort cloud is the first major physical manifestation of the black hole's presence that would be visible to the naked eye. The whispers of gravitational waves and orbital shifts would be replaced by the silent, shimmering beauty of 1,000 comets. It would be a moment of profound change, a shift in the cosmic epoch, a new chapter in the story of our solar system. And as we watch this silent, stunning ballet unfold in our imaginations, we can take comfort in the thought that even in the face of immense destructive power, there is still a quiet, undeniable beauty to be found. It is the beauty of chaos, the beauty of change, the beauty of the universe as it constantly reinvents itself, the silent, beautiful chaos in the Oort cloud. The new celestial light show of comets would be the first hint that something was profoundly different. But the black hole's journey would continue inward, its influence no longer a distant theoretical force, but a tangible growing pressure on the very structure of our solar system. The cosmic stage, once so vast and empty, would begin to feel crowded, and the next to feel the full weight of this unseen presence would be Neptune, the lonely king of the outer solar system and the very fabric of the solar wind that flows around it. Imagine a majestic solitary ship sailing on a vast ocean. For eons, it has followed the same course, guided by the familiar currents and winds. Now, a massive unseen underwater mountain is slowly rising in its path, changing the currents and altering the very direction and strength of the winds. Neptune is that ship, and the black hole is that unseen mountain. As the black hole enters the inner fringes of the Oort cloud and passes into the Kuiper belt, its gravitational pull on Neptune would become strong enough to be detected, not just by its orbital changes, but by its physical effects on the planet itself. Neptune's orbit, a stately 165-year journey around the Sun, would become more elliptical, more eccentric. The planet would be pulled and stretched by the black hole's tidal forces. While we wouldn't see a dramatic change in its appearance, our instruments would detect a subtle growing wobble in its axis of rotation. The powerful winds on Neptune, the fastest in the solar system, would also be subtly altered. Imagine the black hole's gravity as a gentle, continuous push on the planet's atmosphere, a new weak current added to the existing powerful storms. It's an example of a small, persistent force having a cumulative effect on a massive system. It's a beautiful thought, the idea that a cosmic interloper could be rewriting the weather patterns on a planet billions of kilometers away. This brings us to a fascinating and little-known scientific detail about the solar system, the solar wind itself. The Sun is a constant fountain of charged particles, a stream of electrons and protons that radiates outward in every direction. This solar wind is what creates the auroras on Earth and shapes the tails of comets. It's the breath of our star. The black hole's immense gravity would act as a new kind of filter for this solar wind. As the wind flows outward, it would be subtly bent and deflected by the black hole's gravitational field, creating a kind of a quiet shadow in the river of particles. Our spacecraft, like the New Horizons probe, which is currently in the Kuiper Belt, would be the first to detect this change, measuring a slight dip in the density of the solar wind as the black hole passes between it and the sun. It would be a moment of profound revelation, a feeling of being in the shadow of something we cannot see. The philosophical implications of this are quite beautiful. The solar wind is a symbol of the sun's life, its constant outpouring of energy. The black hole, in its silent passage, would be casting a shadow on that life, a temporary eclipse of the sun's reach. It's a reminder of the fragility of our systems, of how a perfect billions of years old balance can be altered by a new, powerful force. And yet, there is no malice in this. The black hole is not an enemy. It is a force of nature, a quiet, powerful visitor passing through. It's an important distinction, the difference between a natural disaster and a malevolent act. The universe, in all its chaotic beauty, is not judging us. It is simply being. This journey to the outer planets is a good opportunity to touch on a scientific mystery that still puzzles physicists, the nature of gravity itself. We know how it works thanks to Einstein. We know that it's a curvature of space-time, but we don't know why. We don't have a good theory that unites gravity with the other three fundamental forces of nature: electromagnetism and the strong and weak nuclear forces. This is the search for a unified theory of everything. And it's a problem that has eluded the greatest minds of our time. The black hole's passage through our solar system, with its immense and localized gravitational field, would be a perfect natural experiment. It would provide us with new data, new extremes to test our theories against. It would be a moment of pure, unadulterated science, a chance to get a step closer to understanding the very fundamental rules of our universe. The black hole's presence would also have a subtle effect on the orbits of the many icy bodies in the Kuiper Belt, the ring of minor planets and comets that lies beyond Neptune. This is the domain of Pluto and other dwarf planets. Their orbits would begin to shift in a more noticeable way than those of the Oort cloud comets. The black hole, now a powerful gravitational presence, would be a new dominant voice in this celestial chorus, pulling on these small icy worlds and setting them on new, unpredictable paths. It would be a moment of quiet drama, a new set of rules being written in the cold, distant regions of our solar system. As we imagine this slow-motion celestial event, we can find a sense of comfort in its scale. This is not a sudden cataclysmic event. It is a slow, methodical journey that unfolds over generations. We as humans would have time to watch, to study, to learn. It would be a moment that unites humanity, a shared experience of witnessing a cosmic event that forces us to look up at the night sky and ask fundamental questions about our place in the universe. The silent arrival of this black hole is not just a scientific event. It is a cultural one, a profound and beautiful story that we would all get to share together as a species. It's a quiet gift from the universe, a chance to stop to look and to wonder. The gravitational influence of the black hole, now a distinct and undeniable presence in our solar system, would not stop its inward march. It has shaken the Oort cloud, perturbed the orbits of Neptune and Uranus, and cast a subtle shadow on the solar wind. The next grand act of this cosmic drama would unfold closer to home in the realm of the gas giants, a place of swirling storms and ancient powerful forces. The black hole's primary dance partner in this part of the journey would be the colossal king of our solar system, Jupiter. Imagine a master sculptor with an invisible chisel of immense power beginning to carve a new form into a mountain of swirling gas. That is the black hole's effect on Jupiter. With a mass more than 2.5 times that of all the other planets in our solar system combined, Jupiter is a giant in every sense of the word. Its immense gravity has a powerful hold on its dozens of moons and a protective influence on the inner solar system deflecting comets and asteroids with its powerful pull. But now it would be Jupiter's turn to be pulled. The black hole's gravity would begin a titanic tug-of-war with Jupiter, a quiet battle between two of the most powerful forces in our celestial neighborhood. The most noticeable effect of this battle would be the tidal forces. Remember how we talked about tides on Earth? The black hole would exert a far more powerful and persistent tidal force on Jupiter. The giant planet, a vast swirling ocean of hydrogen and helium, would begin to be stretched and compressed by this new gravitational pull. This would not be a catastrophic event, not at first. The changes would be subtle, a slight increase in the intensity and frequency of its atmospheric storms. The Great Red Spot. A storm that has been raging for centuries might begin to change its shape, its edges pulling and stretching in response to the unseen forces. It would be a moment of quiet, powerful change, a new chapter in the life of a storm that has outlasted all of human civilization. This brings us to a fascinating and lesser-known fact about Jupiter. Its gravity is so powerful that it's actually a source of heat. As the planet's immense mass slowly compresses itself, it releases gravitational potential energy as heat, a process that contributes significantly to the planet's internal warmth. The black hole's tidal forces would add to this a new source of energy that would subtly increase Jupiter's internal temperature. It's a cosmic feedback loop, a new gravitational force, creating new heat, which in turn might create new, more powerful storms. It's a beautiful example of how interconnected the universe is, and how a distant event can have a profound and unexpected impact. The philosophical implications of this are also quite profound. For as long as we have been watching it, Jupiter has been a symbol of immense powerful stability, a constant in the ever-changing sky. The black hole's arrival would shatter that illusion. It would show us that nothing in the universe is truly stable, that even the most powerful of giants can be swayed by a new powerful force. It's a reminder that change is the only constant, and that even the oldest and most powerful systems are subject to the will of the cosmos. The unsolved mystery here is about the long-term stability of a system of this scale. What happens to a gas giant when its delicate billions of years old equilibrium is suddenly disturbed? The black hole's passage would be a live experiment, a chance to see how a gas giant responds to a new powerful gravitational influence. The black hole would also have a profound effect on Jupiter's numerous moons. The 4 Galilean moons, Io, Europa, Ganymede, and Callisto, are a miniature solar system in themselves, locked in a delicate dance of orbits. Io, the most volcanically active body in the solar system, is a perfect example of tidal forces at work. Jupiter's gravity constantly pulls and stretches Io, creating immense internal friction that melts its interior and fuels its volcanoes. The black hole's arrival would add a new layer to this. It would be like adding a second equally powerful conductor to an orchestra, a new voice that would subtly alter the rhythm and harmony of the Galilean moon's dance. The tidal forces on Io would increase, potentially leading to even more powerful volcanic eruptions. The icy crust of Europa, which we believe hides a vast subsurface ocean, might be stretched and cracked, a new series of fissures opening up in its ancient frozen surface. The black hole's journey through our solar system would be a testament to the power of gravity. We often think of gravity as a simple force, the thing that keeps our feet on the ground. But on a cosmic scale, it is a sculptor, an artist, a musician. It shapes planets, creates moons, and orchestrates the grand ballet of the solar system. The black hole, in its silent, powerful passage, would be a masterclass in the art of gravity, a living, breathing demonstration of its profound and beautiful power. The subtle stretching of Jupiter, the increased volcanic activity on Io, the quiet rumblings beneath Europa's ice, these would be the physical manifestations of a new powerful voice in our celestial choir. And as we imagine this, we can find a sense of quiet awe, a feeling of being a small part of a universe that is constantly in motion, constantly changing, and constantly revealing its beautiful, terrifying secrets. The great gravitational ballet between the black hole and Jupiter, a dance of immense forces, would be a sight of staggering power. But the cosmic journey continues. The silent intruder, this unseen architect of celestial change, would now set its sights on the next great player in our solar system's drama, Saturn. As the black hole passes by Jupiter, its gravitational wake would continue to spread, and the beautiful, delicate structure of Saturn's rings would be the next canvas for its invisible artistry. Imagine a vast, delicate sheet of glass suspended in perfect stillness, and a powerful, invisible force begins to pass beneath it. The glass wouldn't shatter instantly, not with a sound you could hear. Instead, it would begin to ripple, to stretch, and to twist in strange and beautiful ways. This is the fate of Saturn's rings. These rings are not solid. They are a magnificent cosmic mosaic composed of billions of individual particles of ice and rock, each one following its own perfect tiny orbit around the planet. The stability of this system is a testament to the balance between Saturn's gravity and the centrifugal force of the particles' orbits. But now a new force would enter the equation. The black hole's immense tidal forces would begin to stretch and pull at these particles. The parts of the rings closer to the black hole would be pulled more strongly than the parts farther away, a differential pull that would begin to tear the rings apart. The pristine defined edges of the rings would blur. The gaps, which are maintained by the gravity of Saturn's shepherd moons, would become distorted and chaotic. The beautiful, delicate structure would begin to unravel, a slow-motion catastrophe that would unfold with a terrifying silent grace. The ice particles would be flung from their ancient orbits, some pulled toward the black hole itself, others sent hurtling in new directions, a spiral of glittering dust and ice. This phenomenon is a perfect example of a scientific fact that is both beautiful and terrifying: the temporary nature of celestial structures. Saturn's rings are not permanent. They are believed to be the remnants of a destroyed moon, and over millions of years, they are slowly being pulled back into the planet by gravity. The black hole's passage would simply accelerate this process, a momentary glimpse into the long, slow death of a celestial masterpiece. It would be a reminder that even the most breathtakingly beautiful things in the universe are destined to change. The unsolved mystery here is about the true origin and lifespan of these rings. The black hole's interaction would give us a new powerful data set to study their dynamics, a chance to better understand their history and their ultimate fate. The philosophical implications of watching this celestial beauty unravel are profound. We, as humans, have always been drawn to the beauty of Saturn's rings. They are a symbol of cosmic elegance, of the natural order of the universe. To see them distorted and torn apart, not by a sudden violent collision, but by the quiet, inexorable pull of gravity, would be a deeply moving experience. It's a reminder that even in the face of what we perceive as destructive change, there is still a powerful, undeniable beauty in the process. The rings wouldn't just disappear. They would transform into a new chaotic, but equally beautiful spiral of glittering light, a testament to the black hole's power and the resilience of the cosmos. The black hole's influence would also be felt on Saturn's many moons, particularly its larger ones, like Titan and Enceladus. Titan, with its thick atmosphere and hydrocarbon lakes, might experience an increase in its tidal forces, leading to more moonquakes and potential changes in its atmospheric pressure. Enceladus, a small icy moon with plumes of water vapor erupting from its surface, is another perfect example of tidal forces at work. The black hole's additional gravitational pull would increase the squeezing and stretching of this moon, potentially leading to a temporary increase in the intensity and frequency of its famous geysers. We would be watching in real time how a new gravitational force could literally shake a moon and alter its geological activity. The journey of the black hole from the distant whispers in the Oort cloud to the magnificent, terrifying spectacle of Saturn's rings being torn apart is a story about the cascading nature of gravity. Each interaction builds on the last. Each subtle change becomes a profound transformation, as the black hole gets closer. The solar system is a vast interconnected machine, and the black hole is a powerful new gear that would begin to spin everything in a new direction. The elegant clockwork precision of our celestial neighborhood would give way to a new kind of cosmic dance, a more chaotic and unpredictable ballet. And as we watch, we would be humbled by the realization that our perfectly ordered solar system is just a temporary state, a brief moment of quiet in a universe that is constantly in motion. The stunning unraveling of Saturn's rings would mark a profound turning point in the black hole's journey. Its presence, once an abstract concept known only to a few, would now be a visually undeniable force, a new, powerful voice in the choir of our solar system. The gravitational chaos having swept through the outer reaches would now move inward, and the next to feel its touch would be the inner sanctum of the solar system, the rocky planets. Imagine a group of dancers, a trio, in a delicate, elegant waltz. They have been moving in perfect harmony for billions of years, their steps choreographed by the powerful gravitational pull of the sun. Now imagine a new powerful partner slowly entering the stage, a silent dancer with an immense gravitational pull of its own. The trio would not stop dancing. Their waltz would simply change. This is the fate of Mars, Earth, and Venus. The black hole's influence, now a tangible and significant force, would begin to shift their orbits in a new unpredictable way. The effects would be subtle at first, a quiet deviation from the expected path. We are talking about changes that would be measured not in days or hours, but in minutes and seconds over the course of centuries. Mars, the red planet being the outermost of the rocky planets, would be the first to show these changes in a measurable way. Its orbital period, a journey of approximately 687 Earth days, would begin to oscillate, sometimes taking a little longer, sometimes a little shorter, as the black hole's gravity either pulls it forward or holds it back. The delicate balance that maintains its orbit would be disturbed, and the planet would find itself in a new, slightly more erratic celestial dance. This would be a profound moment for astronomers and for humanity as a whole. Our models of the solar system, which have been perfected over centuries, would suddenly be proven incomplete. We would have to rewrite the books, recalibrate our understanding of celestial mechanics. It would be a moment of great humility, a reminder that even our most cherished and established scientific truths are always subject to revision in the face of new information. The unsolved mystery here is about the long-term chaotic nature of a multi-body gravitational system. The orbits of the planets are not a perfect stable loop, but a complex chaotic dance. The black hole's arrival would simply be a new powerful voice in that chaos, a voice that would make the future of our orbits even more difficult to predict with absolute certainty. The philosophical implications are profound. We have always thought of our solar system as a fixed, reliable clock. The sun rises and sets with predictable regularity. The seasons change with a steady rhythm. The planets follow their paths with a silent, beautiful grace. The black hole's arrival would shatter that illusion. It would show us that our clock is not a perfect machine, but a living, breathing system constantly in flux. It's a reminder that even the most fundamental aspects of our existence, like the length of a year or the change of seasons, are not guaranteed to be permanent. One of the fascinating and little-known scientific facts that would come to light is the black hole's effect on the Lagrange points of the planets. Lagrange points are 5 points in space where the gravitational forces of two large bodies like the sun and a planet cancel each other out, creating a stable or semi-stable pocket where smaller objects can reside. Think of the Trojans, the asteroids that share Jupiter's orbit gathering at its Lagrange points. The black hole's immense gravity would disrupt these points, pulling on them and making them less stable. The Trojans, the asteroids in our own Lagrange points, would begin to be dislodged, a new source of potential chaos, and a beautiful demonstration of how a three-body gravitational system can be a fragile and delicate thing. The inner sanctum, the home of the rocky planets, would be a place of growing unease. we would be able to see the effects of the black hole, not just with our instruments, but in the subtle changes to the planets themselves. While the changes would be too small to be seen with the naked eye, a new era of space exploration would begin. We would send new probes to Venus and Mars, not just to study their atmospheres and geology, but to measure their orbits with unprecedented precision, to watch in real time how their paths are being altered by the silent, powerful visitor. It would be a moment of shared purpose for humanity, a collective effort to understand and adapt to this new reality. The arrival of the black hole in the inner solar system would also raise new questions about the security of our planet. While the black hole itself would not collide with us at this point in its journey, the increasing gravitational chaos would increase the odds of a stray asteroid or comet from the Oort cloud or the Kuiper belt being sent hurtling toward Earth. It's a sobering thought, a reminder that while the black hole is not a malevolent force, its presence can have a profound and dangerous effect on our lives. But even in this thought, there is a kind of beauty. It would force us to be more vigilant, to be more proactive in our defense of our planet. It would unite us in a common goal, a collective effort to watch the skies and protect our home. The gravitational disquiet in the inner solar system, a subtle but undeniable sign of the black hole's approach, would grow steadily more pronounced. The orbits of Mars, Venus, and even our own planet, a silent ballet that has been in perfect harmony for billions of years, would begin to show the signs of a new powerful gravitational influence. It is here in our celestial backyard that the black hole's journey would become a deeply personal event for humanity. The most profound effect, the one that would alter the very fabric of our lives, would be the change in Earth's orbit. Imagine a giant woven tapestry, and each thread represents a path through space-time. The Earth's thread has been following the same beautiful elliptical pattern around the sun for eons. Now imagine a powerful unseen hand, gently but inexorably pulling on that thread, changing its curvature and altering its path. This is the black hole's effect on our planet's orbit. The change would not be a sudden violent yank, but a slow, gradual drift. Our year wouldn't change by a day, not at first. The change would be measured in minutes, then seconds, then fractions of a second. But over the course of centuries, it would become a new profound reality. This is a beautiful example of the scientific concept of a three-body problem, a classic puzzle in celestial mechanics. The orbits of two bodies like the Earth and the Sun are relatively easy to predict. But when you add a third body like a black hole, the system becomes chaotic and unpredictable. The black hole's gravity would interact with the Sun's and Earth's in a way that is incredibly difficult to model with absolute certainty. The unsolved mystery here is about the long-term stability of our solar system itself. The black hole's presence would simply be a new powerful variable in an already complex equation, a moment of chaos that would force us to confront the limits of our own predictive power. The philosophical implications of this are staggering. For all of human history, the length of a year has been a constant, a fundamental measure of time. Our calendars, our seasons, our cultures are all built around this constant rhythm. The black hole's arrival would shatter that illusion. It would be a moment that forces us to confront the fact that our most fundamental measures of time are not permanent, but are subject to the whims of a vast and indifferent cosmos. It's a reminder that we are not the masters of our universe, but simply a part of it, subject to its beautiful and terrifying laws. One of the fascinating and little-known scientific facts that would come to light is the black hole's effect on Earth's perihelion and aphelion. Perihelion is the point in our orbit where we are closest to the Sun, and aphelion is the point where we are farthest away. The black hole's gravity would subtly shift these points, altering the shape of our orbit. This would have a profound effect on our seasons. While the tilt of our axis is the primary cause of seasons, the distance from the Sun also plays a role. A change in our perihelion and aphelion would alter the intensity of our summers and winters, a new subtle climate change that would be entirely of cosmic origin. It's a reminder that even the weather on our planet can be influenced by events billions of kilometers away. The black hole's tidal forces, while still incredibly small at this distance, would begin to have a measurable effect on Earth. We would see a slight but persistent increase in volcanic and seismic activity. The immense gravitational pull would stretch and compress our planet, a new kind of stress on the tectonic plates. It's a sobering thought, a reminder that the quiet, beautiful rhythm of our planet is a delicate thing, a balance that can be disturbed by a new powerful force. And yet, there is a kind of beauty in this as well. It would be a new opportunity for geologists and seismologists to study the inner workings of our planet, a new data set that would help us to better understand the forces that shape our world from the inside out. The black hole's passage through our solar system would be a test of our resilience, a moment that forces us to adapt and to learn. We would have to develop new ways of tracking and predicting the orbits of the planets, new calendars to account for the changing length of the year, and new ways of understanding the forces that shape our world. It would be a moment of great intellectual and cultural change, a turning point in our history. The quiet, gentle, and utterly relentless passage of this cosmic object would be a new chapter in the story of humanity, a story about our ability to confront the impossible and to find a sense of wonder and awe in the face of change. The black hole's journey, now a matter of planetary significance, would not stop at the orbits of the rocky planets. Its ultimate destination, its primary dance partner, is the very heart of our solar system, the Sun. As the silent wanderer draws closer, its gravitational influence, once a subtle ripple, would become a direct and powerful force on our star. It is here that we would witness a phenomenon of cosmic proportions, a quiet battle of giants that would change the very nature of the Sun's gentle embrace. Imagine a grand glowing furnace burning with perfect unwavering intensity for billions of years. This furnace is the Sun, and its power comes from a delicate, beautiful balance of forces. On one hand, the immense inward pull of its own gravity tries to collapse it into a single dense point. On the other hand, the outward pressure from the incredible heat and energy of its nuclear fusion, the constant merging of hydrogen atoms into helium, pushes against that collapse. This is hydrostatic equilibrium, the perfect balance that keeps our Sun a stable, life-giving star. Now imagine a new powerful gravitational force, the black hole, adding its pull to this equation. The black hole's gravity would not pull a chunk of the Sun away, not at this distance. Instead, it would act as a new powerful inward force, a gentle squeeze on the entire star. This squeeze would increase the pressure and temperature at the Sun's core. The result? The Sun's nuclear fusion would become slightly more intense. The rate at which hydrogen is converted to helium would increase, and the Sun would begin to burn just a little bit brighter, a little bit hotter. The change would be minuscule at first, a fractional increase in its overall luminosity, a difference that would be measured only by our most sensitive instruments. But over time, it would become a profound and undeniable reality. This is a beautiful example of a scientific truth that is counterintuitive. A gravitational squeeze can lead to more heat and light. It's a reminder that the universe works in beautiful, intricate ways that we often don't consider in our day-to-day lives. The unsolved mystery here is about the long-term effects of such a change on a star. What happens to a star's lifespan when its core fusion is altered even slightly? Would it burn out faster, or would it simply find a new stable equilibrium? The black hole's passage would give us a chance to study stellar physics in a way that is simply not possible from a distance. The philosophical implications of this are profound. The Sun is a symbol of stability and life, a constant in our ever-changing world. The black hole's arrival would show us that even our most fundamental source of energy is not a static object, but a dynamic living star that is constantly responding to the forces around it. It's a reminder that nothing is truly permanent, and that even the stars themselves are subject to the will of the cosmos. The Sun's gentle embrace would become a tense grip, a new kind of power that would alter the very light that reaches our planet. One of the fascinating and little-known scientific facts that would come to light is the black hole's effect on the Sun's solar flares and coronal mass ejections. The Sun is a turbulent, violent place, constantly spewing out massive amounts of charged particles and energy. The black hole's tidal forces would stir this turbulence. The intense gravitational pull would create new stresses in the Sun's magnetic field, potentially leading to a temporary increase in the frequency and intensity of solar flares. While the black hole itself wouldn't be a source of these flares, its presence would act as a powerful catalyst, a cosmic kind of spoon, stirring the Sun's immense churning surface. This would be a moment of great concern for us on Earth, as more frequent and powerful solar flares could disrupt our power grids and satellites. It would be a stark reminder that while the black hole is not a malevolent force, its very presence can have a profound and dangerous effect on our lives. The Sun's gentle life-giving light would be forever changed by this encounter. The change would not be a catastrophic one, not a sudden dimming or a fiery explosion. It would be a slow, gradual shift, a new, slightly more powerful rhythm to the beat of our star. The length of our days, the intensity of our summers, the very light that reaches our eyes, all of these things would be subtly altered by the quiet, inexorable passage of the black hole. And as we imagine this, we can find a sense of quiet awe in the fact that our star, a source of such immense power and stability, is not an island, but a part of a vast interconnected universe, a beautiful and terrifying tapestry of forces that we are only just beginning to understand. The black hole's journey, now a matter of direct influence on the Sun, would bring with it a new kind of silence. But this silence would not be empty. It would be a profound, powerful absence that would paradoxically reveal the black hole's presence in a spectacular way. We are talking about the absence of light, a phenomenon that would be announced not by its own existence, but by its stunning effect on the light of everything else. This is the luminous curtain of the event horizon and the beautiful mind-bending effect of gravitational lensing. Imagine a funhouse mirror, but one made not of glass, but of the very fabric of space-time. As the black hole approaches, its immense gravity would begin to bend the path of light from distant stars and galaxies, warping and distorting the image we see. This is gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. The black hole would act like a cosmic lens, a giant magnifying glass that would bend the light around its unseen form. The stars behind it would not disappear. Instead, they would be stretched into long, thin arcs rings and multiple images, a ghostly and beautiful halo of light surrounding the black hole's silent presence. The very darkness of the black hole would be outlined in a shimmering, distorted tapestry of starlight. This would be a moment of stunning visual confirmation, a moment where the invisible becomes visible not by its own light, but by its effect on the light of others. The black hole's arrival would be a profound lesson in the nature of reality. It would show us that what we see is not always the truth, but simply a perception of it filtered through the curvature of space-time. The unsolved mystery here is about the nature of the event horizon itself. What exactly happens at the point of no return? Is information truly lost forever, or is it encoded in some way? This is the core of the black hole information paradox, a problem that has puzzled physicists for decades. The black hole's presence in our solar system would be a new, profound opportunity to study the nature of this final frontier, a chance to get a step closer to understanding the greatest mystery in modern physics. The philosophical implications of this are immense. The gravitational lensing would be a reminder that our universe is not a simple flat canvas, but a dynamic, curved, and complex reality. It would be a reminder that our perception is not the final word on what is real. The black hole, in its silent, lightless passage, would be a master teacher, using its very darkness to illuminate the most profound truths about the nature of our universe. The luminous curtain of its event horizon would be a beautiful and terrifying sight, a visual representation of the boundary between what we can know and what is forever hidden from us. One of the fascinating and little-known scientific facts that would come to light is the black hole's effect on the cosmic microwave background CMB. The CMB is the faint afterglow of the Big Bang, a uniform bath of radiation that fills the entire universe. As the black hole passes through our solar system, its immense gravity would subtly alter this background. It would create a tiny, almost imperceptible cold spot, or a hot spot, in the CMB as it passed by, a subtle echo of its journey that would be forever imprinted on the cosmic canvas. This would be a beautiful and profound reminder of the black hole's reach, a testament to the fact that its influence extends to the very edges of the observable universe. The black hole's visual presence, outlined by the stretched starlight, would also have a profound effect on the way we see our sun. As the black hole passes in front of the sun, it would not create a traditional eclipse. Instead, the sun's light would be bent around the black hole, creating a shimmering, distorted ring of fire, a ghostly halo of solar plasma. The sun would not be gone, but its light would be twisted and warped in a way that would be both beautiful and terrifying. It would be a visual representation of the power of gravity, a moment that forces us to re-evaluate our understanding of the universe and our place in it. The silent, beautiful passage of the black hole, outlined by the luminous curtain of its event horizon, would be a moment of shared awe for humanity. It would be a moment where we are all forced to look up at the night sky and confront a beautiful and terrifying truth, that the universe is vast and full of secrets, and that sometimes the most profound truths are revealed not by light, but by its absence. The gravitational lensing, the shimmering, distorted halo of light, would be a visual confirmation of the black hole's presence, a new kind of celestial landmark. But the black hole, in its quiet, inexorable passage, would not only bend light, it would also bend time. This is the mind-bending phenomenon of time dilation, a concept so profound it forces us to reconsider our most fundamental understanding of reality. Imagine two clocks. One is on a mountaintop, and the other is at the bottom of a deep valley. A little-known scientific fact is that the clock in the valley, being closer to the center of the Earth's gravity, actually runs a tiny bit slower. The difference is so small it is measured in nanoseconds, but it is real, and it is a testament to Einstein's theory of relativity. Now imagine a gravity well so deep and so powerful that it makes the Earth's seem like a mere dimple. This is the black hole, and as it gets closer, its effect on time would become a profound and undeniable reality. For a person on Earth, time would continue to flow as it always has, but for any object approaching the black hole, time would begin to slow down. Think of it as a river. The water in the main channel flows at a constant, steady pace, but as the water approaches a powerful whirlpool, its motion becomes slower and more chaotic, a swirling dance that seems to resist the forward motion of the river. The closer you get to the center of the whirlpool, the slower the water seems to move. The black hole's gravity would be that whirlpool, and time would be that river. An object orbiting the black hole or falling toward it would experience time at a different rate than we do on Earth. A minute for us could be an hour for them. A day for us could be a year. This is the essence of time dilation, a beautiful and terrifying consequence of immense gravity. The philosophical implications of this are staggering. For all of human history, we have thought of time as a constant and unstoppable universal river that flows at the same rate for everyone everywhere. The black hole's arrival would shatter that illusion. It would show us that time is not a constant, but a variable, a flexible thread in the tapestry of space-time that can be stretched and compressed. It would be a moment that forces us to confront the fact that our shared experience of time is a local phenomenon, a beautiful but temporary truth that is only valid in our corner of the universe. The unsolved mystery here is about the nature of time itself. Is it a real physical dimension, or is it an emergent property of our consciousness? The black hole's passage would be a new, powerful piece of evidence to help us answer this profound question. One of the most beautiful and heartbreaking aspects of this phenomenon is the fate of things that fall into the black hole. From our perspective on Earth, we would never see an object cross the event horizon. We would see it get closer and closer, its image getting redder and dimmer as its light loses energy fighting the black hole's gravity, a process known as gravitational redshift. We would watch it slow down its motion, becoming slower and slower, a frozen image of a celestial object suspended forever at the edge of the abyss. This is because from our point of view, time for that object has slowed to a complete stop at the event horizon. It's a tragic, beautiful, and utterly profound illusion, a cosmic farewell that we would never get to see completed. The silent, time-bending passage of the black hole through our solar system would be a moment of shared awe and deep contemplation. It would be a moment that forces us to confront the most fundamental truths about our universe and our place in it. The black hole is not just a destructive force. It is also a beautiful and profound teacher, using its very existence to illuminate the deepest, most mysterious laws of our cosmos. And as we imagine its slow time-bending journey, we can find a sense of quiet wonder in the thought that our universe is stranger, more beautiful, and more complex than we could have ever imagined. The silent, time-bending journey of the black hole would be a testament to its immense power. But as it draws closer to our sun, another more terrifying phenomenon would begin to take hold. The gentle, almost affectionate squeeze of its tidal forces would become a violent, relentless pull, a force so powerful that it could rip apart anything, a comet, a planet, even a star. We are talking about the ultimate expression of tidal forces, a process so bizarre and so powerful, it has its own name: spaghettification. Imagine a long, thin strand of spaghetti. Now imagine a force that could stretch that strand into an even thinner, longer thread until it eventually snaps. This is what would happen to any object that gets too close to the black hole. The reason for this is simple, yet profound. Gravity is not a uniform force. It gets stronger the closer you are to the source. So as an object, say a comet or a stray asteroid, gets pulled toward the black hole, the part of the object closer to the black hole would be pulled more strongly than the part farther away. This difference in gravitational pull would create an immense stretching force, a tidal force so powerful it would literally tear the object apart atom by atom and stretch it into a long, thin stream of matter, a cosmic noodle of dust and gas. The philosophical implications of this are immense. We are so used to thinking of objects as solid, as stable as things that hold their shape. The black hole's spaghettification effect would shatter that illusion. It would show us that even the most solid and stable objects are just temporary arrangements of atoms, and that in the face of an immense gravitational force, they are as fragile as a house of cards. It's a reminder that the fundamental laws of physics can be both beautiful and terrifying, and that our understanding of reality is often limited by our own human-scale experience. The unsolved mystery here is about what happens to matter at this extreme. Does it truly get stretched into an infinite thread, or does it eventually get heated to a point where it becomes a plasma? The black hole's passage would be a new, profound opportunity to study matter under the most extreme conditions, a chance to get a step closer to understanding the true nature of the universe. One of the fascinating and little-known scientific facts that would come to light is the black hole's effect on the sun's accretion disk. While the black hole itself would not have an accretion disk as it passes through our solar system, its gravity would begin to pull matter from the sun's outer corona and the solar wind, creating a temporary glowing ring of superheated plasma around its event horizon. This would be a sight of stunning, terrifying beauty. The black hole, once a silent ghost, would now have a voice, a visible halo of light and fire that would announce its presence to all. The light from this disk would be a new, powerful source of radiation, a beautiful but deadly reminder of the black hole's power. It would be a moment of profound change, a new chapter in the story of our solar system, and a testament to the fact that even a silent, dark object can have a profound and luminous effect on the world around it. The silent, beautiful passage of the black hole outlined by the luminous curtain of its event horizon And the terrifying spectacle of spaghettification would be a moment of shared awe and deep contemplation. It would be a moment that forces us to confront the most fundamental truths about our universe and our place in it. The black hole is not just a destructive force. It is also a beautiful and profound teacher, using its very existence to illuminate the deepest, most mysterious laws of our cosmos. And as we imagine its slow time-bending journey, we can find a sense of quiet wonder in the thought that our universe is stranger, more beautiful, and more complex than we could have ever imagined. The black hole's journey, now a breathtaking and terrifying spectacle, would not last forever. Like a ghost ship passing through the night, it would continue on its path, its immense gravitational power reaching its closest point to the sun and then beginning to recede. The cosmos, in its quiet, relentless way, would reassert its order. The chaos would begin to subside. The cosmic hum of gravitational waves would slowly fade. The magnificent, terrifying light show of spaghettification and gravitational lensing would begin to disappear. We are now in the final act of this celestial drama, a quiet goodbye from a celestial friend. Imagine a powerful dark storm that has been raging for months. The winds have howled, the clouds have roiled, and the world has been changed by its passage. But then, as suddenly as it began, the winds begin to calm. The clouds begin to part, and a new, different kind of light begins to shine through. This is the feeling of the black hole's departure. Its gravitational pull, once so strong, it bent the fabric of space-time, would begin to weaken as the distance between it and our solar system increases. The effects it has had from the orbits of the outer planets to the fusion in our sun would not simply vanish. They would remain a permanent scar on the face of our solar system, but they would no longer be actively changing. The new cosmic dance would have been established. The philosophical implications of this are immense. The black hole is not a malevolent force. It is not an enemy. It is a force of nature, a quiet, powerful visitor passing through. Its departure is a reminder that even the most profound and destructive events in the universe are not personal. They are simply a part of the grand, beautiful, and chaotic story of the cosmos. It's a moment that forces us to confront the fact that we are not the center of the universe, but simply a part of it, subject to its beautiful and terrifying laws. The unsolved mystery here is about the long-term permanent effects of such an event. How long would it take for the solar system to find a new equilibrium? Would the orbits of the planets ever truly stabilize again? Or would they be forever locked in a new, more chaotic but still stable dance? The black hole's departure would be a new profound opportunity to study the long-term dynamics of a multi-body gravitational system. One of the fascinating and little-known scientific facts that would come to light is the black hole's gravitational wake. As it passes through our solar system, its gravity would have pulled on the sun and the planets, giving them a slight increase in their overall velocity. The entire solar system would be moving a little bit faster, a quiet, invisible nudge that would be a permanent testament to the black hole's visit. The sun would no longer be at the exact same location in the galaxy relative to its original path. It would be on a new, slightly altered trajectory, a new kind of cosmic history being written in the silent language of gravity. The orbits of the planets would also be permanently altered. The black hole's passage would have shifted their aphelions and perihelions, giving them new, slightly more elliptical paths. The length of our year, the intensity of our seasons, all of these things would be permanently changed. We would have to adjust our calendars, our scientific models, and our understanding of the universe. It would be a moment of great intellectual and cultural change, a turning point in our history. The quiet, gentle, and utterly relentless passage of this cosmic object would be a new chapter in the story of humanity, a story about our ability to confront the impossible and to find a sense of wonder and awe in the face of change. The silent, beautiful passage of the black hole from its quiet arrival to its graceful departure would be a moment of shared awe and deep contemplation. It would be a moment that forces us to confront the most fundamental truths about our universe and our place in it. The black hole is not just a destructive force. It is also a beautiful and profound teacher, using its very existence to illuminate the deepest, most mysterious laws of our cosmos. And as we imagine its slow time-bending journey, we can find a sense of quiet wonder in the thought that our universe is stranger, more beautiful, and more complex than we could have ever imagined. The cosmic farewell. A quiet goodbye from a celestial friend would be a new beginning, a new chapter in the long, beautiful story of our solar system. The black hole's journey from a silent, gravitational whisper to a cosmic farewell would leave our solar system forever changed. The quiet goodbye, a slow-motion parting that spanned centuries, would be a new beginning, a new chapter in the long, beautiful story of our celestial home. The chaos would subside, the magnificent light show of gravitational lensing and spaghettification would fade into memory, but the effects of the visit would remain a permanent legacy etched into the very fabric of space-time. This final section is a moment of reflection, a quiet contemplation of the aftermath and the profound cosmic legacy of the black hole's visit. The orbits of the planets, the very rhythm of our celestial dance, would be permanently altered. The black hole's immense gravity, like a sculptor's chisel, would have reshaped the paths of our worlds, giving them new, slightly more elliptical trajectories. Our year would be a different length, our seasons would have a new rhythm, and our calendars, a human invention that we thought was a perfect reflection of the cosmos, would have to be forever changed. This is a beautiful and humbling thought, a reminder that the universe does not conform to our human-made rules. It simply is. The new solar system, with its slightly more chaotic but still stable orbits, would be a living, breathing testament to the black hole's visit. It would be a new kind of cosmic clock, a new rhythm for us to learn and to live by. The philosophical implications of this new reality are profound. We would have to confront the fact that our solar system, our home, is not a fixed, unchanging place, but a dynamic living system that is constantly being shaped by forces beyond our control. It's a reminder that change is the only constant, and that even the most fundamental aspects of our lives, the length of a day, the passing of a year, are subject to the whims of a vast and indifferent cosmos. This shared experience, the knowledge that we all lived through a cosmic event that forever changed our home, would be a new kind of unity for humanity, a new story that we all get to share. It would be a moment that forces us to look up at the night sky, not with a sense of perfect order, but with a sense of wonder, awe, and a little bit of beautiful chaos. One of the fascinating and little-known scientific facts that would come to light is the permanent disruption of the Oort cloud. The black hole's passage, a violent cosmic broom, would have flung trillions of icy bodies from their ancient orbits. This would create a new long-term influx of comets into the solar system, a constant parade of icy wanderers that would continue for thousands, if not millions of years. The night sky for generations to come would be a new brilliant spectacle, a beautiful and terrifying reminder of the black hole's visit. It would be a new kind of celestial navigation, a new set of data for astronomers to study a new chapter in the long, beautiful story of our solar system. The cosmos would have been permanently rearranged, and the new arrangement would be a testament to the beautiful, terrifying power of gravity. The scientific legacy of this event would be immense. We would have a new, unprecedented understanding of black holes' gravity and the dynamics of a multi-body system. We would have new data to test our theories of general relativity, new insights into the nature of space-time and the event horizon, and new questions to ask about the fundamental laws of our universe. The black hole's passage would be a new kind of textbook, a living, breathing demonstration of the most profound and mysterious laws of physics. It would be a moment of great intellectual and cultural change, a new chapter in the story of humanity, a story about our ability to confront the impossible and to find a sense of wonder and awe in the face of change. The silent, beautiful passage of the black hole from its quiet arrival to its graceful departure would be a moment of shared awe and deep contemplation. It would be a moment that forces us to confront the most fundamental truths about our universe and our place in it. The black hole is not just a destructive force. It is also a beautiful and profound teacher, using its very existence to illuminate the deepest, most mysterious laws of our cosmos. And as we imagine its slow time-bending journey, we can find a sense of quiet wonder in the thought that our universe is stranger, more beautiful, and more complex than we could have ever imagined. The cosmic farewell. A quiet goodbye from a celestial friend would be a new beginning, a new chapter in the long, beautiful story of our solar system. And so the journey ends. The cosmic traveler, the silent, powerful ghost, has moved on, continuing its own solitary path through the inky blackness of the galaxy. Our solar system, our beautiful, fragile home, is forever changed. A new kind of history, etched into the silent dance of the planets. The whispers of its arrival and the roar of its presence have faded, replaced by a new quiet rhythm, a new kind of harmony that is both familiar and profoundly new. I'd like to gently ask one last time, where is the place you're staying now? The time in that place at this very moment, how is it flowing? I hope that for a little while, our shared journey has brought a sense of calm, a feeling of being a small part of something vast and beautiful. Thank you for listening, for dreaming with me in the deep darkness. May your mind be as clear as a star-filled sky, and your heart as full as a universe of possibility. If you enjoyed our time together, please consider subscribing. It's a small thing, but it helps me to continue to share these stories with you. Now it is time to rest. Let the final thoughts of our journey slowly fade, like a distant star winking out in the night. Let the quiet hum of the universe be your lullaby, and the gentle rhythm of your own breath be your guide. Sleep well, my companion, wherever and whenever you are. Sweet dreams.